Good afternoon, everyone, and welcome to our final session of Crypto 2024 on authenticated key exchange protocols. Our first talk is by Stanislav Yaretsky, and the title is Bear Pake, Universally Composable Key Exchange from Just Passwords.
Thank you. Hello, how are you? Good afternoon. This is a joint work with Manuel Barbosa, Kai Gellert, and Julia Hesse. So the problem of password authenticated key exchange is functionality studied for quite a while, starting with Beloved Merit. Two people submit passwords, and they either get a fresh, secure random key if the two passwords are equal, or they get independent keys otherwise. And this has been a subject of many works, and the efficiency of these protocols in standard group setting is like essentially the same as Diffie-Hellman key exchange. It basically already started with the encrypted key exchange of the Beloved Merit. And this is the recent candidate that was chosen by the IETF in the PEG competition, CPACE. There is a recent interest, so this is about the standard groups, but if you want to do it post-quantum secure, there is quite a lot of interest in that. And in particular, this construction is generic from any CAM or a key exchange. Let me review security models that were proposed for PEG. So initially, Bellare, Poincheval, Rockaway proposed a game-based model that assumed uniform passwords. Boyko, Mackenzie, Patel created a simulation-based model where actually passwords, this model could deal with arbitrary password distributions, a very positive feature in this context. And Canetti et al. 2 years later essentially lifted this model and cast it in a framework of Canetti's framework of universal composability. And this became a gold standard for, maybe it should be gold standard, not golden, I don't know, of what PEG security should be, in particular, really, because it connects two things of arbitrary password distributions and at the same time universal composability. And in particular, in our interactions with IETF, this was an explicit requirement that we have UC proofs. A few years later, a few years ago, Abdallah et al., we also relaxed this universal composable model in certain way to emulate the kind of commit, but reveal the commitment only after the protocol terminates, and this allowed this whole class, in particular this one, that was chosen by the IETF, to show that they are universally composable as well once you admit this relaxation. Now, with relaxation or without the UC PEG model of Canetti et al. And those follow-up works, they have subtle assumptions on additional inputs. And the assumptions, people who work with universal composability framework are aware of this, but maybe others not so much. They assume a unique session identifier that has not appeared anywhere else in the system, that parties have unique identifiers of themselves. Not only that they remember who they are, and it makes some sense, semantics within the application, but also that this identifier never appeared before, is not used by any other honest party. And also that they know who it is that they talk to. And functionality as codified in this paper and used ever since has these requirements in addition to the natural requirement of password equality. And for example, by contrast, a game-based model of Bellare et al. Actually did not pose these requirements. So in some sense, they are artificial. So the true functionality looks like this. People submit all sorts of unique identifiers in addition to this password, and the functionality checks that all of this stuff holds. One unfortunate outcome is that the beast, if you prove this secure, as everyone does, and was supposed to, then you don't know about security of an honest party who happens to reuse this session ID, or perhaps whose party identifier was used by somebody else. The model just does not make claims about that. Now, these requirements are just standard in the UC framework, and that's how they were. That's why they were basically cast into this particular application of the UC framework. And in some sense, it's no problem from theory point of view, because they're indeed very easy to satisfy. This is no problem. These things, if they are supposed to be unique, then let's just pick them at random before the protocol starts. So this was a General Canetti's recommendation. Okay, how do you get these unique identifiers? Just pick them at random. I mean, that's explicit regarding session identifiers. The party identifiers, it's like you're not supposed to, but like if you don't know what to do, then pick them at random. At least it's unique. So Ada can pick hers, and Charles can pick his, and they exchange, concatenate the nonces. At this point, SID is unique, and my counterparty matches your party, your counterparty matches my party. It's all good. Moreover, this just takes one protocol flow, because the second flow can be piggybacked on whoever goes first in this protocol, right? So this is just one extra flow, and you're good. But people don't really like to have a useless extra flow, right? Like, so if you're an engineer, I don't think you're happy. Like that, okay, the theoreticians tell you, you have to have this extra flow. And you're like, why? And we don't really know why. Because we basically have only lame answers. They ask, do you really need this extra flow? And we say, well, the proof's needed. We don't know if the protocol's needed. We actually don't think that they do. Can it be an empty string? Well, what about if I don't know, like let's say I just equate them to IP addresses because I don't know what to do. I don't know how to populate these strings. Well, but they are reused and sometimes hidden by the firewall. So you just, you make a mess if you try to satisfy this requirement. So there is a gap. In practice, we don't want to use them. In theory, we have to use them. This is reflected, for example, in Abdallah at Hase and Julia Hesse. They, specify CPACE for in IRTF after it won the competition, so that the implementation is clear. And they say it is recommended that you have this SID, or you should have the party identifiers. So you might or you might not. There is a gap between what's proven and what people end up implementing. So we create this model that is a bare peg. So bare because it has no, it is password only. Okay, it's stripped from these additional identifiers. So session identifier is there, but it's an output, not an input. And counterparty the same way. And party identifier is, of course, an input, but it's arbitrary. So if you don't have it, it's fine. If you can set it any way you like, it doesn't matter that it was reused, that somebody else, for example, used the same IP address as you are now presently located at, right? And we think it's the best of models because it takes all these good features of the game-based and at the same time as you see, so it has these features. And Victor Schupp also had a model that partly does what we want, mostly actually, and we indeed take some mechanics from, we end up copying some of his mechanics in our proposed functionality. There is also the general work for how to avoid these, but it doesn't seem to apply to minimum round protocols, and also it doesn't seem to apply for idealized models of analysis, which we all use in these particular protocols. So we showed that this stripped away model actually is equivalent to the old model in the following sense. If you have the stripped one, it's very easy to implement what people used to want, which is the old PEG. Just concatenate everything you have to the password, right? And also this whole like one round pick random stuff shows that if you have the bare peg, if you have the peg, you know, they can be also thought of as bare pegs, except that they cost extra round. And we showed that anything created from encrypted key exchange applied to non-interactive key exchange gets you a bare peg, and in particular CPACE, chosen by the ITF, is also secure in that setting. And as a bonus, we noticed that once you strip the PEG functionality from these additional identifiers, then what happens is that, you see, Ada only wants to run on certain PEG, on certain password, and if she sort of doesn't have a fixed sense of who she wants to talk to, she will discover who she talks to in the protocol, and if she doesn't like it, she will reject. But the funny consequence is that she actually could do the same protocol now with Debbie, with Eddie, with Francis, and right? And so all these protocols, they are single simultaneous flow. So everybody just sends one message. And now you can have n-square parties establishing session, n parties establishing n-square pairwise authenticated keys at the cost of a single broadcast. And actually very small, they're like single group elements or single public key. Assuming that they also, so we think like maybe Internet of Things would be nice to do this way. But so the next talk is very much on this topic as well, right? So, but take a very different take on it. So here is our model. It is slightly simplified on this talks, on this slide. And I just want to also make a shout out to, Ran Canetti updates his framework. And in particular, there is something very nice that, will happen in this rewrite, addition or version, that is a nice way to split your functionality between a shell that handles all the cryptographically irrelevant stuff of routing versus the body that is routing oblivious. So in particular, a party gets a new session and it does not know with whom, because the cryptography layer does not care. The outer layer does. Of course, a party has to know whom to send the message to, right? But that's very nicely split in this. So, in case you are curious, go and check. We are conformant with this framework, and in particular, this allows us to divorce the routing stuff from the crypto. And we do have a global identifier, but to conform with the UC setting, but it's global. It's not unique per instance, right? And the functionality does, what you maybe expect. If somebody wants to run a session on a password with some identifier for themselves, and it's an arbitrary associated data, the adversary learns that they are doing so, and the associated data is revealed, but not the password. And now adversary has just two choices. He can actively attack a session with some choice of single password guess, and the key in case the password was correct. And he can determine what's the session ID on that attack session and what's the counterparty that this attack person would output. But it has to be that the session ID has never appeared in the system before. So you cannot be fooled to think that you have the same session as some other one, for example, that honestly executed. Actively attack session must have different sessions from others. Or he can passively connect two different parties with some session, again, has not appeared before, unless he does it first for Ada Charles, Charles Ada, right? At which point it does what you expect. The two keys, the two passwords that these people ran it are compared, and either the random key is copied or they get independent key. Key differences from the old model. Because parties are not attached to any identifiers, it has this kind of what we call free dating, adaptive avenue for the attacker. He can, suspecting that we all run on the same password, he can connect you to a random person in the room of his choice. And this is something that was not happening in the old UC-PAKE, where you committed to certain SID, certain PID that no other honest person would use. No two different honest persons would use. Also, this is the reusability part. We have no limit of how many times some participating party is going to be bombarded with messages and how many sessions it outputs, either passively connected or actively. Of course, the application can say, I only want to establish 20 sessions, that's it. But it's up to the applications. The crypto can give you a choice. Like if you want to establish a key with everybody in this room, you can. Okay. So here is the compiler from encrypted key using encrypted key exchange, the same merit idea, but applied to non-interactive key exchange. We must assume that this key exchange has keys which are anonymous. So, I mean, they're not anonymous, sorry. They're just uniform over some domain for which we have an ideal cipher. And this is, for example, satisfied by the LWE-based Nike that recently appeared. We combine the two and we get UC bear PAKE. If you instantiate this Nike with the old hash Diffie-Hellman, then you get a security under CDH or under GAPDH. It's actually tight. And also, if you just want standard PAKE, which gives you one time in some sense, right? You don't reuse, then it's secure under slightly weaker assumptions still. And there is a caveat. This paper by Freire et al., they use, in analysis of Nikes, they use names, which we strip here. So we assume a simplified model. So technically, these things proven about hash Diffie-Hellman as a Nike, in some sense, have to be reproven because you need to strip identifiers. So we use public keys as identifiers, and that's not syntactically how they analyze, for example, this protocol. Here is the construction, and it's not surprising if you have Nike. What is this? Is you create public key, private key pairs. You encrypt using ideal cipher the public key, because that's the domain of the ideal cipher, your key under a password. And when that cipher, and everybody does it symmetrically, when that cipher arrives at some entity, Ba, which was supposed to be Bob, he decrypts it under his password. And if the passwords are the same, then of course, this key is the same as the one Ada chose, right? And then they just finalize a Nike. But the novelty in some sense is that, that it can be reused, right? So we show security if Ada sends one cipher and then she actually receives many of these ciphertexts, and she will just output keys and session identifiers for every ciphertext she got, until the application says, I'm done, that's enough. Okay, so I don't have time for this tiny intuition for why this actually works. And this notion of security, by the way, is by Cash et al. For Nikes. And here is just a small flash of how CPACE works. It's specifically a Diffie-Hellman-based key agreement where, interestingly, the public parameters, the base of the discrete logarithm, is created using password hash. Otherwise, it's just a Diffie-Hellman key exchange. So it's a Diffie-Hellman key exchange on parameters which are derived from by hashing a password. And so this works, again, you can reuse. And we showed that this reuse bare peg without any identifiers is as secure as the old one, which was one time and assumed the identifiers. It's secure under the same assumption. So I will finish with, OK, that's what we do, and maybe some questions. For example, we don't do this for any CAM, which would be interesting, right? So Nike, it exists based on LWE, but CAMs are, of course, more standard and less expensive as of now. Maybe we can reduce the ideal cipher assumption, perhaps with these type of ideas. Maybe we can have a standard model construction. We should also remove sys from other functionalities, like, for example, opaque.
Thank you. Thank you very much. All right, so we are over time, so we'll move on to the next speaker and encourage you to speak with Stash afterwards.
Oh, there it is. Hi.
All right, the next speaker in our session is Michael Rosenberg, who will be speaking about Lotkey, a framework for constructing identity-based pegs.
Thank you. Yeah. My name is Michael Rosenberg. I just got my PhD. Thank you. And this is joint work with one of my advisors, John Katz. So we saw a PEG from the previous talk, so I'll do this quickly. A PEG is a key exchange protocol wherein two parties use mutual knowledge of a possibly low entropy secret in order to derive a high entropy shared secret. The properties are such that a passive adversary has essentially no advantage at getting this, at deriving this shared key K, and an active adversary can make at most one password guess per session. As a side note, this is a very odd setting to be in. We can make cryptographic statements in a setting where there are no authenticated channels, no secure channels, and not even high entropy anything. This is very odd and leads to kind of odd consequences in our analysis, which we will see later. So how PEGs are used in a bunch of different things. So we'll focus on PEG and IoT specifically. Some IoT protocols give the password to every single device in say, a mesh network. And they use mutual knowledge of the password in order to authenticate and set up a secure channel with each other. The issue here is that is what we call catastrophic impersonation. So if you have an attacker which, say, breaks into a smart light bulb, they get a dump of the password and then can impersonate themselves to the router as a thermometer, right? So you have one device is compromised, and yet now every single device in this network can be impersonated. So the solution to this, well, the actual solution to this is to be an adult and use PKI. But the solution from prior work is to instead bind an identity into your password in a kind of irreversible way, so that now every single device has a unique password file that is inextricably bound to their identity. So if they're broken into, you can only impersonate them themselves. So the way this works, and we'll identify this binding function as just F. So now every single device has their own password file linked to their personal identity. And when an adversary breaks into the light, they will get the light password file and be able to impersonate the light bulb, but not being able to impersonate the thermometer because that would require them to crack the password, which is something that you can do, but it's significantly harder than the previous case, which is you get it for free. So this construction is called Identity Binding Password Authenticated Key Exchange. This is a crypto paper by Kramers, Now, Haas, and Ronen. So the IPAKes that they present in their paper are called CHIP and CRISP. They roughly have the structure of having an identity-based key exchange protocol using this function f, which we haven't defined yet, and then passing the output through opaque, and then using that key as your final session key. Notably, both of these protocols, CHIP and CRISP, rely on Diffie-Hellman type assumptions, and I will argue that they rely on them inextricably. It doesn't seem that you can make this not rely on Diffie-Hellman. So in particular, this means that you can't have a post-quantum construction that looks like CHIP or CRISP. So the contribution of this paper is Latka is the first post-quantum IPAKE. It is significantly more generic over both of these underlying primitives than CHIP. Its construction is based on CHIP. It's actually a transformation of the underlying protocol. I have the transformation here. Let's see if this renders properly. OK, great. So this supports any kind of pre-quantum or post-quantum IBKE or PAKE. It also works in the pre or post-specified peer model. So for example, if Alice and Bob don't know each other's identities beforehand, they can learn each other's identities and then continue the protocol. That's the post-specified peer model. And this also is very generic over the security properties of the underlying IBKE. You don't need any specific form of the Kennedy-Kraft-Chick model. It kind of works with all of them, which is kind of surprising. We also implemented this, and the post-quantum version has a 3% slowdown over pre-quantum CHIP, which is pretty nice. So like I said, Latka is based on CHIP, so we will look at CHIP first. So recall, what we want to do is have this binding function. We want to bind an ID to a password in a way that's hard to reverse. This sounds a lot like identity-based cryptography. So the usual flow for identity-based cryptography is that you have two parties or multiple parties, and you have a centralized party, a trusted third party, called the Key Generation Center, the KGC. The KGC will generate a main key pair, MPK and MSK, and then a party will ask them, they will say, I am Bob, please give me a secret key. They will extract a secret key based on Bob's identity and give it back to Bob. And Alice will do the same thing. And then they can use just knowledge of each other's identities, of MPK, and of their own private keys in order to derive a shared key. So how does CHIP use this in a password context? So in particular, the thing that it needs is if two parties know the same password, they should be able to communicate with each other. In addition, we need to make sure that every single ID gets a unique password file, so you can't impersonate arbitrary people. And that compromising a party only reveals the password file itself and not the password or anything that could be used to derive more password files. So the first requirement we can get by simply running the IBKE key generation using random coins derived from the hash of the password. The second property we get by simply extracting to ourselves using knowledge of MSK. And then the third property, which is you should only reveal the password file when compromised, you get this by simply deleting the things that you no longer need. So Bob does this, and Alice does this. And this is quite odd, right? You have removed the third party from identity-based cryptography, which is kind of the entire point of identity-based cryptography. This is a very weird scenario. The last step of CHIP is you have to pass everything through opaque. You need that for forward secrecy. Bonus points if you can tell me why you need opaque and not, for example, key confirmation to get forward secrecy. So there's a problem with this construction. and that this is really particular to the kind of IBKE that you use. Consider an IBKE where the first message contains MPK. This is perfectly secure. You can, if you have a secure IBKE, you can just add this if you want. However, this is completely insecure to use with chip. And the reason why is because, recall, MPK is a function of the hash of the password. So if you send a public key, you get your password cracked. So in this setting, in this low entropy PAKE setting, your public keys are private keys, which is kind of odd. So the property that chip requires is that the transcript of the IBKE is independent of the coins used in the key generation process. There are a few IBKEs that do this, but no post-quantum ones that do this. So we take some inspiration from a previous PAKE-like construction. It's called the omega method augmented PAKE. So Thank you. So an augmented PAKE is a PAKE where the client has a password, but the server has a password file. So it's kind of on the way to IPAKE. There is no identity binding built in. And the omega method is a particular kind of a PAKE which is extremely generic. It only requires a PAKE and a signature scheme, and also symmetric encryption. Briefly, the way it works is, say Bob is the client, so he has the password. Alice, to generate her password file, will hash the password twice, derive a signing key pair, use the second hash to encrypt the signing key, and then delete the intermediate values. In the online phase, Alice and Bob will run a PAKE over the first hash of the password, derive a key, and now Bob still has to prove that he knows PW itself and not just the first hash of PW, or at the very least he has to prove that he knows the second hash of PW, which he will do by receiving a challenge from Alice. Alice will send this encrypted, signing key, double encrypted. It's encrypted first under the second hash of the password, and then secondly under the PAKE key. Bob knows both of these keys. He knows the PAKE key because he just ran the PAKE. And he knows the second hash because he hashed the password. And so he'll be able to double decrypt this and then use that signing key to sign the entire transcript of the protocol. And Alice will verify. So one interesting thing is, ignore this like ae.enc thing here. If ESK were just sent in this protocol, it would actually leak data about the second hash, right? H2 is used as the encryption key for ESK. So if you could guess the password, you can just attempt try password and then trial decrypt ESK and just keep going. So this has offline, this is clearly not secure. This is insecure against even passive adversaries. So it seems like this encryption step, ae.enc, is sufficient in order to prove the security of this APAKE. Right? If the adversary compromised the PAKE in order to get this K value, then they would already know the hash of the password, at least one of the hashes of the password. And so if it can do this trial decryption, it might learn another hash of the password. But by that time, it could already have started cracking it with the first one. So this actually doesn't benefit it whatsoever. This is a really neat idea. So more broadly, you can use a PAKE at the beginning of your protocol to set up a secure channel and then run the rest of the protocol, which is possibly leaky, inside of that secure channel. So that's what we do. So the setup for Latka is identical to chip. And the first step is you just set up a secure channel, just like the omega method. And in particular, using MPK instead of a hash of a password. Remember, MPK is a function of the hash of the password, so this is fine. It's just a little more efficient. And you set up this secure channel under this the PAKE key K, and then you run any IBKE inside of this secure channel. Some important details I'm leaving out are how do you define this secure channel, especially in a way that is secure under adaptive corruptions in the UC model. This requires a little bit of work. Also, there are no PQ IBKEs defined, but actually making them is not that difficult. You can go from an AKE to an IBKE, or you can go from an AKE with KCI resistance to an AKE with KCI resistance and forward secrecy, which you need, and then turn that into an IBKE. So there's a bunch of generic steps that you can take that are pretty efficient. And of course, the security notion of IBKE, which I just discussed. Also, because this IBKE is encrypted, you get identity concealment against passive adversaries for free. And if you use an identity concealing IBKE, you get security from active adversaries, at least on one side. We benchmarked this. We implemented a bunch of PAKEs and a bunch of IBKEs, some of them pre-quantum, some of them with post-quantum encryption, some of them with post-quantum encryption and authentication. This is what the Sigma R protocol looks like. It's a 6-round protocol. It's one of the more complicated versions of this. And for believability, I ran this on my old home router. The results are pretty promising. The pre-quantum LATCA is 4% slower than CHIP, and the post-quantum is only 3% slower. If you want fewer rounds, you will have to pay more, though. The 2-round version is 1.56 times the runtime, but overall, these are pretty comparable numbers. For future work, we want to look into strong IPAKE. So that's for strong. So these strong constructions in general mean that you are simply pre-computation resistant. So an adversary cannot gain any advantage at cracking a password by doing some pre-computation before they compromise one of the parties. Both of these have a minimum round number of 2. It'd be interesting if you could get lower than 2. Also, it's not clear how to make a hybrid IPAKE. So if you make a hybrid IBKE and a hybrid PAKE, then you could reasonably have a hybrid IPAKE. We have hybrid IBKEs. We don't have any hybrid PAKEs. So that seems to be the barrier here. Bonus points if you can tell me why the obvious parallel PAKE scheme doesn't work. And for full transparency, please don't work on this. I have 2 papers on this, and I really want to go to Madrid. Some final notes. I spent almost 1.5 years on this paper. The first version of it was so broken that I scrapped the whole thing. The only thing that remains is its name. There's just a lot of fun detail in the paper. LATCA is actually 2 IPAKEs. We needed 2 separate constructions, very slightly different for the pre and post-specified peer model. Also, we used cake, which is a PAKE that you construct from just a wide block cipher. You can construct it from a wide block cipher in Sabre, which is a chem. It's really fast and cool that you can do that. We had to slightly modify the ideal functionality of IPAKE. It's relatively small, though. Also, CHIP had a flaw, like a very subtle flaw in their proof of security, and we discussed with the authors of CHIP, and we have a patch for the proof in one of our appendices. If you find this cool, please take a look at the paper, and with that, I'll take questions.
Thanks very much, Michael. If you have a question, please come to one of the microphones at the front.
Thanks for the nice talk. You mentioned the hybrid PAKE. Can you explain what's that?
Yeah, sorry. By hybrid, I mean like hybrid post-quantum, as in using assumptions like Diffie-Hellman in addition to, say, lattice assumptions.
Okay, thank you.
So I have one question. So you mentioned a post-quantum version built from Sabre. Are there challenges in building the same thing from Kyber and Alchem?
Yes, at least for cake. So cake requires an ideal cipher, and defining an ideal cipher. So all of these Kyber public keys, for example, are mod Q, and so the way that you would have to define an ideal cipher is define a keyed permutation function over a big int that is something like, something mod like q to the e for some exponent e. And so defining a permutation like that on big ints is a lot harder than just defining a wide block cipher that operates on byte strings. There are other pakes though. For example, Sheik uses the HIC, and that works with Kyber with a lot less fuss.
All right, well, if there are no other questions, please join me in thanking Michael again. Okay, the next talk in our session is by Xuanji Su, and it is entitled Fine-Grained Non-Interactive Key Exchange Without Idealized Assumptions.
Okay, thanks for the introduction. I'm Su Chuanjie from UESTC. And our title is a Fine-Grained Non-Interactive Key Exchange Without Idealized Assumptions. It's a joint work with Wang Yu and Pan Jiaxin. This work, we focus on the fine-grained multi-party non-interactive key exchange whose security is based on very mild assumption or even without any complexity assumptions. First, I want to start with an overview of the non-interactive key exchange. The non-interactive key exchange in the two-party setting is a method by which two parties exchange and can share the secret key without needing to interact with each other. Each party can independently generate their secret key and public key and use the public key from the other party to compute the shared key. The existing two-party NIKE key are constructed based on various assumptions. This includes well-established assumptions like Diffie and Hellman assumption. In a three-party setting, each party exchanges public keys and computes the shared key by using the secret keys generated by themselves. A known candidate of the three-party NIKE key is proposed by Juice based on the bilinear Diffie and Hellman assumption over pairings. When extending to n-party setting, all known candidates against any polynomial adversaries are constructed based on the multilinear map or in the world of Opusotopia. So it's natural to ask whether we can construct multi-party NIKE key based on weaker assumption. Very recently, Afshar et al. Answered this question affirmatively by introducing a fine-grained multi-party NIKE key based on the random oracle or multilinear generic group model. Their constructions are in the context of fine-grained cryptography. Now I'm going to review about the fine-grained cryptography. Instead of secure against any polynomial adversaries, the fine-grained cryptography requires the adversaries have limited resources and the honest party do not possess more resources than the adversaries. One of the motivation of the fine-grained cryptography is to have the security based on very mild assumption. The existing works on the fine-grained cryptography are mainly constructed in three computational models. The first is a bounded parallel time model. In this model, there have been several primitives constructed based on no assumption or NC1 not equal to parity L/poly. And the second is bounded time model. In this model, there exists key exchange based on random oracle, exponentially strong one-way function, and average case hard 0 k-click. And there also exists a multi-party NIKE key based on the random oracle and the multilinear Schup's generic group model. A concurrent and independent recent work by Bohr et al., which will be introduced in this track later, also proposed a fine-grained four-party NIKE key based on the exponential secure injective pseudorandom generators and sub-exponential hardness of CDH, or based on the non-uniform exponential secure injective pseudorandom generators and the multilinear Morse generic group model. The third is a bounded storage model, and there exists key exchange based on node assumption. So this brings us the central question: can we construct multi-party NIKE key based on very mild assumption or without any complexity assumption in these three models. We answer these questions affirmatively and show three results. The first result is a construction of multi-party Nike based on the boundary parallel time model, which is based on the assumption of NC1 not equal to parity L/poly. And this scheme is secure, and this scheme is computable in AC02 and secure against adversary in NC1. Here, the AC02 includes circuits with constant depths, polynomial size, and unbounded fan-in using AND or NOT and parity gates. The NC1 includes circuits with logarithm depths, polynomial size, and fan-in 2 gates. Also notice that the AC02 is included in NC1. And the parity L/poly includes log space Turing machine with parity acceptance. Our starting point of this work is to utilize the fine-grained hash-proof system to construct a fine-grained two-party Nike. Roughly, we let the projection and the statement of the hash-proof system serve as the public key in the two-party Nike, and let the parties share the proof with the witness and the secret verification key. And its security is based, and its security is guaranteed by the smoothness of hash-proof system. When extending to multi-party setting, the key pairs are vectors generated by different types of algorithm. When more parties are involved, it's unclear how to combine a bunch of vectors to generate a session key. So a strawman solution is to extend the vectors to matrix. Taking the three-party case as an example, the first party has the secret key SK1 and the PK1, which equals to SK1 times public parameter matrix M. And the second party has SK2 and PK2, which equals M times SK2. And the third party has SK3 and PK3, which equals to M times SK3. And the parties share the multiplication of SK1, M, SK2, M, and SK3. For the third party, since he has known SK3 and PK1, to compute the shared key K, he has to know SK2 times M. To address this issue, we need additionally publish the multiplication. However, this will result in too much leakage on SK2 and compromise the security proof. So to overcome this, we exploit the power of the symmetric matrix. More specifically, we compute M prime with a transpose of M times M and replace M by M prime. We also generate secret keys from the uniform distribution over symmetric matrix. Thanks to the symmetry of the matrix, the third party knows transpose of public key, and so which is exactly the SK2 times M prime. This enables each party to compute the shared key and ensure the correctness. However, in this construction, the smoothness of hash-proof system cannot be used for security proof, since secret keys are not uniformly random. To find a counterpart compatible with the symmetric matrix, we prove the core lemma, which says that M prime times SKI is indistinguishable to M prime times SKI, then plus an identity matrix I. And we refer to our papers for the detailed proof. By using the core lemma, the multiplication of SK1, M prime, SK2, M prime, and SK3 is indistinguishable to SK1. The multiplication of SK1, M prime, SK2, SK2, then plus I, and M prime times SK3, then plus I, which will be in the form of SK1 times M prime times R, then plus I for some random matrix R. A nice property of this form is that the last column and row vector in the matrix must be outside the span of M prime. So we can then prove the bottom right bit of the results is a proof with smoothness. So it's a random bit, and we set it as the key. We can also running our scheme in multiple times in parallel, and each party can so that each party can share a session key with any polynomial size, without increasing the complexity of the circuit depth. Our second result is a multi-party NIC key in the bounded time model based on the average case hard 0 k click. This scheme is computable in tilde O lambda to the power of number of users NP plus k, then -1, and is secure against adversaries in tilde O lambda to the power of NP plus k. We first review about the average case 0 k click. This hypothesis generally says that finding the correct solution requires essentially solving all instances. Based on this assumption, Lavini et al. Construct a two-party NIC. In their constructions, the two parties exchange lists of instances, out of which has square root number of instances with having at least one solutions. By the birth state paradox, there would be a single instance in common having at least a solution. So the parties can share the index of the common instances. When extending to multi-party setting, a strawman solution is to let all parties to exchange the lists and share the common index of the instances. The primary challenge lies in that the rapid increase in the error probability of correctness as the number of users increase. So we increase the number of instances with solutions. And as the number of instances increases, the number of common indices also increases. So we further share the sum of the overlapping part. For a rigorous analysis of correctness, we exploit a set of indicators. Each indicator denoted by yi equals 1 if the ith index chosen by the last party is also chosen by all other parties, and equals 0 otherwise. Without loss of generality, we assume the indices chosen by the last party are genuinely independent. This guarantees the independence of these indicators. And we also let the indices chosen by all other parties are independent, but condition on all distinct. This ensures the probability that the indicator equals 0 is small. By computing the probability that all indicators equals to 0, we can obtain the correctness is satisfied with high probability. For security, the reduction aims to find the correct solution by making use of an adversary who breaks NIC. To simulate a view of the adversary, the reduction splits the list into multiple ones, then plunks other solutions into the list. Previous work has shown that there exists a splitting algorithm that can split the list into list pairs. So in a multi-party setting, we also propose a generalized splitting algorithm that can split one instance into multiple ones by introducing a binary structure to use the original splitting algorithm. However, the generalized splitting algorithm also produces incorrect instance lists with different solutions, and we solve it by introducing additional efficient checking. And we also noted that our construction can be amplified to a stronger, our security can be amplified to a stronger one by using the Goldreich-Levin extractors. Our third result is a construction of multi-party NIC in the bounded storage model, and which is based on no assumption. This game is in this game, the honest users consume O lambda to the power of NP memories, and against adversaries with memory bound, O lambda to the power of NP plus 1. In the bounded storage model, each party stores a set of bits in a long uniform random string. Once the uniform random string disappears, the parties exchange the indices, then save bits in common. The crucial point is that the intersection of the indices are also pairwise independent, so the shared bits have high entropy. This allows the parties to apply the privacy amplification. To ensure efficiency, the parties utilize the strongly two universal hash functions, and the security is guaranteed by the pairwise independence of the indices from the intersection. For correctness, we need to guarantee that the size of intersection is sufficiently large. So to achieve this, we also exploit the indicators, which is similar to our zero-click-based construction. The main difference is that we only prove the indicators are pairwise independent rather than completely independent. So and provide a lower bound of their sum. So we firstly change the approximately pairwise indices into the perfectly pairwise indices. And this ensures the pairwise independence of the indicators. We also let all other indices are approximately pairwise independent. And this ensures each indicator equals 1 with high probability. Then we can apply Chebyshev's and Markov's inequality to show the size of intersection is sufficiently large with high probability. This result holds when the indices are perfectly pairwise independent. However, this only makes the sum smaller and hence does not affect our result. We note that all of our constructions satisfy a nice property we call the extendability. By using the conversion technique proposed by Bonnet and Waters, we can convert our multi-party Nikes with extendability into the bit-fixing pseudo-random functions. And by using the generic technique proposed by Hornfeist, we can convert the bit-fixing pseudo-random functions into a multi-party Nike identity-based Nikes. This is the end of my talk. Thanks, and I'm happy to answer any questions.
All right, we have time for some questions. So if you have a question, please come up to one of the microphones. Okay, well, seeing none, then we'll thank our speaker again, and we'll move on to the next talk. Thank you very much.
Thanks.
Ready.
It's going to be the previous slide.
The final talk in this session is by Elahi Sadeghi on fine-grained non-interactive key exchange revisited.
Thank you for the introduction. Hi, everyone. I know that everybody is probably tired of the conference and all the talks, including myself, so I'm going to try my best to keep this last one short. This is a joint work with Balthazar Barra and Geoffroy Couteau. So fortunately, the background of our work is very similar to the previous talk that we just saw, so I can go over them very quickly. So what was key exchange protocols? They are protocols among a group of parties. They interact and they want to find a shared key, which is going to be hidden from any outside observer. So what is non-interactive key exchange protocols? It's going to be the same setting, where in order to make it non-interactive, we're going to allow the parties to only send one single message simultaneously, and then find the shared key as before. A very useful property of non-interactive key exchange protocols is that any subgroup of parties are going to be able to find a shared key at any time. Okay, great. So what do we know about Nikes? So we have the traditional work of Diffie and Hellman in the 70s, and this work is for two-party Nike. Then after about like 20, 25 years later, we had the first three-party Nike from pairings, and after about like 15 years, we had k-party Nike for k more than 3, but only from I/O and multilinear maps. So the question here is that Nikes are very well-motivated, useful constructions for applications, and can we build these from like weaker assumptions? Can we like relax the requirements, relax the security in some way? In our work, we're going to focus on relaxing the security. We're gonna only consider the adversaries that are going to be bounded polynomial time, which is going to be the study of fine-grained cryptography to review what fine-grained cryptography was. So in traditional cryptography, we consider the security against arbitrary polynomial time adversaries, while in fine-grained cryptography, we consider adversaries that has limited computational power, which, for example, it can be a fixed polynomial time bound. The motivation for using fine-grained setting is that we can achieve a stronger cryptographic primitives from weaker assumptions. For example, there has been work that constructed a fine-grained public key encryption from exponentially secure one-way functions. Okay, so we're gonna study Nikes in this work in fine-grained setting. So there has been work in Eurocrypt last year that constructed a four-party Nike with quadratic security in Shoup's generic group model, but they couldn't prove it from standard assumptions, and they complemented this result with proving that one cannot achieve more than quadratic security in Mauer's generic group model. So just to review the difference between the Shoup's and Mauer's generic groups, I want to say that in Shoup's generic group model, the parties have access to the group elements via some random representation, while in Mauer's model, they don't have access to the group elements. They can only interact with the group oracle. So Shoup's model is going to be a little bit stronger than Mauer's model, which means that between these two results, there is going to be a gap. So a natural question here is going to be that can we build fine-grained Nike with the standard assumptions in the plane model? And a more technical question is that can we actually close the gap between this positive and negative results? In this work, we're gonna answer to both of these questions. We're gonna construct a four-party Nike with quadratic security under sub-exponential hardness of CDH and the existence of an exponentially secure injective PRG. And then we're gonna prove that this construction is going to be sub-quadratically secure in Mauer's generic group model, assuming the existence of an injective PRG. So I want to take a moment here and look at these two results that we have. So at the first glance, it might be a little bit strange. And you might ask that, isn't it the case that our second result is trivially implied by our first result? Or isn't it the case that the security in plane model imply the security in generic group model? So the answer here is no. These two models are incomparable. In generic group model, even though the adversary has limited access to the group oracle, but it has computational power outside this oracle. And in our work, in order to close the gap of the work of ACMS, we need to actually assume an unlimited adversary, because in their work, they had to assume an unlimited adversary in order to prove their impossibility result. And this means that our techniques in our first result does not actually applied in the Mauer's model. So okay, great. We're gonna have an unlimited adversary in Mauer's model, but the strange thing here is that we're assuming a PRG. So a natural question here is that isn't a PRG broken in generic group model when we have unlimited adversary? So surprisingly, the answer here is yes, but I should mention that in our work, we don't assume that a generic adversary cannot break the PRG. What we do is that we actually just prove that if there exists no standard adversary against this injective PRG in the plane model, then we can prove that our construction is secure against this unlimited adversary in Mauer's model. So I hope that this gives you some intuition about our results and why they make sense. And with this being said, I'm gonna jump right into our construction. So the idea of a fine-grained fortnight is to actually finding collisions in the exponents of the group elements. This means that, let's assume we have a group of size n squared. We have 4 parties. Each party is going to send n group elements. So the first 2 parties, P1 and P2, are going to find a collision with constant probability by birthday paradox. And P3 and P4 is going to do the same. And then we can view each pair of parties as one party and do a Diffie-Hellman key exchange and find a shared key. However, this idea, this protocol as it is going to be broken. Why? Because there exists some square root discrete logarithm algorithms in generic group model. And also, to find collisions among the group elements, the number of group elements should scale with the square root of the size of the group. This means that the running time of the adversary is going to be the same as the running time of the parties, which is not good because there is no security gap here. Okay, what the work of so in the ACMS, what they did was to increase the size of the group to n to the power of 4. Then what they did, what their idea was that, so consider the 2 parties, P1 and P2. What they do is that they sample n values as exponents. They're gonna split these values into 2 halves. And then party 1 is going to send the n group elements as before. And along with that, it's gonna send the hash of the first half of its exponents. And party 2 is going to do the same, and but just send the hash of the first half of the exponents. Now they can find a collision between these hashes, and therefore party 2 is going to have the first half of the party 1's exponent, and then it can recover the rest of the exponent by using the catching kangaroo method in linear time. And it's going to be linear time because the size of each half is going to be n squared. And then the 2 parties are going to have a shared secret and public key, which means that if party 3 and party 4 do the same, they can reach a shared key with the previous idea. However, this construction has some limitations. So as you can see, both parties have to send the hash of the first half of their exponents, which means that they need to leak some information about the exponents. This means that they require to rely on some stronger variants of the DDH assumptions. Also, since we need to use the catching kangaroo method in order to recover the exponent, the ACMS work, in their work, they require lots of equality tests. And both of these limitations make them to work in generic group model and random oracle model, which is still not ideal. So in our work, we want to avoid this. And the question is how? So let's go over the idea of ACMS works again. So what they do is that they first sample some random exponents, And then they try to leak some information in order to find the collisions with constant probability. In our work, we're trying to kind of do the reverse. We first sample some short values, and then we try to expand them and use these expansions as the exponents. Or equivalently, we want to sample from a pseudo-random sparse subset of all possible exponents. With that being said, I want to explain the Fourier construction of our work. So we're going to use a length doubling PRG. So consider party 1 and party 2. Each of them are going to sample n seeds, n values. They're going to compute the PRG of these values, which is going to be the exponents that they're going to use. And then they're going to send the n group elements and find the collision and have their shared public and secret key as before. And then party 3 and party 4 can do the same, and the rest of the protocol is the same as before. So in order to argue the security here, we just need to, in the first step, we need to replace these PRGs with a random value. However, we should be careful here because we need to actually embed the collisions in the right position when we replace the PRG outputs with a uniformly random value. And the idea that we come up with here is to force the simulator to force this collision to happen with the same probability as when we had the PRG outputs by embedding them in the distribution. And after this fix, we just need to apply CDH in order to get the security. So this is going to be a full protocol. So party 1 and party 2, after computing their exponents with the PRG, they're going to find their collision. Party 3 and party 4 are going to find their collision. And then we can view each pair as one party and do the Diffie-Hellman key exchange in order to find a shared key for the 4 of them. Okay, now let's prove the security of this protocol in Mauer's model. So in order to find the security in Mauer's model, we have one challenge that I mentioned before. So a generic adversary in Mauer's model can actually break the PRG. So it can distinguish between the PRG outputs and random values, which means that this analysis that we just did won't work in generic group. Our solution here is that we observed that we only need to have the security of the CDH when the exponents of the CDH challenge is coming from the image of the PRG. So we introduce an intermediate assumption, which we call PRG CDH, which is exactly as it sounds. It's a CDH assumption, which the exponents are coming from the image of the PRG. And this assumption can be secure even when the underlying PRG is insecure, which means that this can be very useful in the generic group model. And it means that even if the adversary can break the PRG security, this assumption can still be secure. And actually, this is the case in our work. So in order to prove the security in Mauer's model, again, what we want to show is that if we have an adversary against the PRG in the plane model, then our construction is going to be secure in the Mauer's model. So the steps of the proof is pretty simple. We're going to assume that we have an adversary against this assumption in the Mauer's model, and then we're going to try to use this adversary to construct an adversary against the PRG in the plane model. So let's assume we have an adversary A against this PRG CDH assumption, and this adversary is going to make Q queries. So since we are in Mauer's model, the adversary does not have access to the group elements, which means that the queries that it makes are going to be independent of the CDH challenge. And because of this independency, we can assume that the queries are actually fixed even before seeing the CDH challenge. This means that we can view the list of queries as a non-uniform advice, and then use this non-uniform advice to construct an efficient non-uniform distinguisher for the PRG. So this distinguisher are going to look for collisions among the linear combinations of this given list. So if you think about it, if we have the challenge X, if X is random, then we're not going to find, the distinguisher won't find any collision in this list because we have unlimited security of the CDH in the Mauer's model. But if it's the output of the PRG, with high probability, we're going to find the collision because the PRG is broken here. However, we're not achieving full quadratic security here, and the reason is that we cannot assume a fully exponential secure PRG, and it's because the time-space trade-offs in the non-uniform setting. So that was the security. Now to summarize, we constructed a Fortnite key with quadratic security in the plane model, and we proved that it's going to be subquadratic secure in Mauer's model based on the existence of an exponentially secure injective PRG. The open problems that we have is that, so the first one is the obvious question of, is it possible to fully close the gap of our result and the impossibility result of ACMS? We investigated it a little bit in our paper, and it seems that it relates to the hardness of some combinatorics, some additive combinatorics, and I refer to the paper for more details. And the next question is that, can we construct a post-quantum fine-grained Nike? Interestingly, our construction can be based on LWE and an injective PRG. However, it's going to be broken in post-quantum setting. And the reason is that we need an exponentially secure PRG, which we don't have in the post-quantum setting because of the Gruber's algorithm. So our construction is going to be broken in linear time. And with this, I'm going to conclude my talk, and I'm happy to take any questions.
Are there any questions? Please come up to the microphones if you have one. I was wondering if you could say a little bit more about this, this security, the fact that you can prove security even when the PRG itself is not secure. That seemed a little bit counterintuitive.
Yeah. Okay, this is the confusing part of our work, actually. We got like a lot of questions about it. So here, what's happening is that we don't assume that the PRG is secure in Mauer's model. So we can assume that PRG is secure in the plane model. So with using that, we say that, okay, if we have the PRG broken in the, secure in the plane model, then we can prove that our construction that uses this PRG is going to be secure in Mauer's model. So we don't have this, we don't assume the security of the PRG in Mauer's model itself. We assume the security in the plane model, but we say that if we use the same PRG, the construction is going to be secure in Mauer's model.
All right, well, we'll conclude here. Please join me in thanking the speaker again.
Thank you.
And that brings us to the end of Crypto 2024. Thank you, everyone, for coming. We look forward to seeing you next year back in Santa Barbara for Crypto 2025, and wish you a safe journey home.